Okay, did you get the codes in the mail? Okay, so what are we doing?
I'm trying to figure out the number of quanta for temperature.
Room temperature is good. So what have we done in class? Where did we stop? Oh, hi Diane, happy to see you. So we stopped at partition function for harmonic oscillator, and then we decided that we may want to need the number of excitations in a given harmonic oscillator, number of quanta, if the oscillator is in the thermal equilibrium, right? Why do we need it?
Our phonon modes?
Yeah, but why do we care about number of quanta in the phonon modes?
You have to make the quantum math.
Yes,
but
but
the operator between the system and the bath.
So the warmer the system, the quicker the relaxation. And at the same time, if the system is hot, then it can also heat up if the bath is hot, then it can heat up the system, bring it to thermal equilibrium. So it will be, we are making anything needed to perceive the concept of detailed balance. So if you do remember what we did 2 weeks ago, because last week there were no classes, we were, okay, I'll better talk first and then start scratching on the board. We did anything possible with regular Liouvillean dynamics. We do have operator of Liouville that allows to propagate density matrix forward in time, and it allows for two elementary processes: accumulation of phase and transition between states due to external field. Right? In addition, if we make two tweakings, two additional things, inhomogeneous broadening, average over distribution of frequencies in several systems of the similar nature but slightly different frequencies, then we can do the same equation, but upon average over ensemble we get dephasing for the overall observable. And the second trick, if we assume that external field performs random fluctuations close to like thermal 0-point noise, then we are getting something that looks similar to relaxation of population coming to thermal equilibrium. But those were tricks, not non-rigorous modeling. Right now we want to get through derivations of quantum theory of relaxation, and we will do it in the class. And the main benefit that we expect that we will be able to get relaxation of population to thermal equilibrium for any arbitrary temperature. Not only infinite temperature, not only zero temperature, but any temperature as a parameter. If you take into account the thermal bus at a specific temperature, we will be able to get such terms in the equation of motion for electronic degrees of freedom that will drive it exactly to thermal equilibrium. Make sense? More or less. Okay. So lab differs from lecture by lack of derivations. So I just declare a couple of equations and then without derivations, and then we will go to their practical implementations and getting hands-on experience. I'm trying to focus on the board so that I can write the direction. So this is something that we should have derived by the end of yesterday's lecture. We will complete derivation in the first 3 minutes of tomorrow's lecture. So what it is? This is average number of quanta in the mode of quantized oscillator. If you do have harmonic oscillator in ground state, all population is 100% fed. Or, well, and as soon as we heat it up, there will be like 70, 20, 10%, according to Boltzmann distribution. And if we want to explain it with one number, we will multiply energy times population, and we will see that for such distribution, average number of quanta will be somewhere between the 0 and 1. 0.3 quanta in the system. Does it make sense? Okay. So we may explore how this equation behaves, and of course we can just mathematically draw it based on the function of dependency, but in order to save time, we can just run the code and see how does it look like. So let me invite you to run the code Bose Einstein and see what you observe.
You gotta run the other one first.
No.
Mine crashed. Yeah, if you run the other one first, we can find W.
Okay. You can just type W equals 1.
So 1 capital W?
Yes.
Yeah. What's Bose Einstein?
Mm-hmm. No, just type W. Oh, you're converting it between units.
No, I was just seeing what different values did.
So you just look on this equation as a function of different values of the temperature, and what makes what is important here is not the absolute value of temperature, but the ratio between temperature and the thermal energy, PT, right? So which trends do you see? So when you run the code, there appears two windows with images, and in one we do see the dependence of number of quanta on the energy. So at given energy, if at given temperature, if the energy is increasing, if the energy is becoming bigger and bigger than thermal energy, then the number of quanta presented in the at thermal equilibrium in given oscillator decreases very quickly, right? So approximately is like decreasing exponential. Right now it is on the left panel, the one that pops up if you do it. The right, yes.
What well are we
in?
in? Or is the bath a single?
Right.
Oscillator?
No. Later you will take into account that it has infinite number of oscillators.
Okay,
but
so
right now we are focusing only on one of them.
and the one on the right is causing the first popular, or the first state, or n equals 0.
Figures on the left and right are the same, but the functions are the same, but the arguments are different. I've tried to label them. One is energy over temperature, and another is temperature over energy. So if you look on it as energy over temperature, it shows the higher the energy, the less quanta are present in the mode. If the energy offset of these two levels is bigger than thermal, then at thermal equilibrium, everything will be in ground and almost nothing in the excited. In the first excited, and nothing in the second.
But are we plotting the population?
It's not population, it's number. Expectation value of number of quanta. It is the same as energy, but without scaling factor, without h nu, dimensionless energy. The panel on the right is the same function, but as where the argument is inverse, temperature divided by number of quanta. And I've just plotted it because it is much easier to perceive. So it is almost linear, especially in the limit when the temperature is much higher than energy offset. At the limit of high temperature, this function will just grow linearly. So we are going to derive in the in class how do this thermal distribution of thermal bath contributes to the equation of motion of our electronic system. Again, right now we are just skimming through those derivations. How did we formulate the Redfield operator for 2x2 system. It was 4x4 matrix, right? One, two, one, two, three. And we do not have time to process it, but approximately, how did it look? Where were the zeros? What stop?
Oh, it's very small.
It is very slow. Hmm? This cross camera will be always. It is. It shows the better. It reflects that there is no. I'm not using the camera of the laptop because otherwise it will be too slow. We are using this larger facility. Okay. So there are zeros. At least in these four corners, right? Hmm? Yes, somewhere in diagonal too. And these four corners are most important because they reflect the change in the row 1 and row 2 elements. When we did a little experiment 2 weeks ago in class, we assumed a noisy path, and then we approximately written autocorrelation function of Redfield operator proportional to the square, right? And then I don't care what was here, but in these places we got the and I'm skipping the rest. So this construction was driving change in populations for the row 1 and row 2 elements. Does it, do you recall something like this? It was like Thursday before break. Minus, plus, minus, plus. So this can be interpreted that if we are interested in the evolution of this element, it gets decrement proportional to its present occupation, and it gets increment relative to occupation of the excited state. Okay? Which means if we were in ground completely, there is still the occupation of ground will change from 100% to something bigger. And opposite signs for last row. So the change of occupation for the row 2 will be decreasing proportional to what it presently is, and will be increasing in respect to what was in the ground state. So this construction will give equal measure of change of population for both ground and excited, and they will approach 50% occupation. This is maximal result that you can do from the noisy, classical noisy bus. Right now, our goal is to establish disproportion, to have values here and there a little bit different. We know from intuitively that transitions from higher energy to lower energy states should be more probable, and transitions from lower energy state to higher energy state should be less probable. And we will do it in the class. The result that we are going to obtain will be as follows. So some parameter of relaxation times n. And n is very related to this one. There are some additional details related to the question by Levi, that it will be n of all oscillators from the bath that are matching resonance condition with our electronic transition. It's not one, it's many oscillators. But since they are in resonance, they have the same frequency. So it will be minus gamma n plus gamma n, and here will be plus gamma times n plus 1 minus gamma n plus 1. And also there will be minus gamma 2n plus 1 here, minus gamma 2n plus 1 there. So when we do this construction, it doesn't look as we will in operator before. This again is super operator that is responsible for dynamics of density metrics, but we need to use different letter. Let's call it R for Redfield. Redfield. There is nothing red and there is no field. It is a family name of a guy who derived the equation. And there are several variations of this dissipative matrix equation, master equation, but the idea is that we do have different rates of relaxation and excitation for ground and excited state. And their difference is proportional to number of quanta in the mode of a bath, with or without extra term that equals 1. What are we going to get if the temperature equals 0? What is the number of quanta in the system if temperature equals 0? Huh? How many quanta? No, it will be in the ground state, but number of excitations. 0, right? Everyone agrees? So at time equals 0, or not time, temperature equals 0, we do not have this, don't have this, don't have this, don't have this. So this simplest case of relaxation matrix at 0 temperature, there will be nothing happening for excited state, and the ground state, the occupation from state 2 will be relaxing. It will be disappearing from excited state, therefore we have minus sign. Disappear. And it will appear in the state, in the ground state. Here in ground. So minus gamma plus gamma, and all the rest are zeros in the limit of 0 temperature. Now we do have an idea how the operator that controls relaxation looks in 2 limits: infinite temperature and 0 temperature. And in between, it is defined by the value of this n function. Make sense? I think it is enough. Let's look on the code.
Oh, quick question.
Please.
You don't care if what excited state it's a quantum is in, you just care that there is a quantum in the excited state.
Can you repeat the question? I have some idea, but it may be different
for
from
n equals 1 over the exponential minus 1.
Mm-hmm.
that does not tell you which quanta it is in. I mean, which excited state it's in. It just tells you that there is one in an excited state. No?
Okay, I've got your confusion. I understand what you. I have an idea of what you may want to ask about. So, our goal, our interest, is electronic degrees of freedom for simplest possible model, 2 levels. But it is surrounded by a lot of harmonic oscillators. Harmonic oscillator has more than one excited state. But in this modeling, harmonic oscillator will be not in the eigenstate. It will be in so-called thermal state. That means that occupations will be distributed between each of the excited states with total summation of occupations equals 1, but there will be so many percent. Well, these numbers are sealed, they are not exact. I wouldn't see a specific temperature which gives it, but approximately. More population on ground state, a little less on the first excited, even less on the second excited. And if you do an average, it means that in ensemble, upon average, we have a probability to, the most probable chance is to find the number of quanta somewhere between 0 and 1. Like 0.3 quanta will be found in average. So it is what this parameter n means. So it is, if system would be in the eigenstate, it will be exactly 0 or 1, 1, 2, 3. But now it can be fractional, because it is an average over several occupations, which all are populated.
So it doesn't, and we don't care which state it's populated or which state it's pseudo-populated. We just care that there is an average more than 0.
Yes.
Okay.
And I agree with your saying in everything, except the wording that which state is populated. We do not know. And there is no population on one state. It is distribution of probability that each of them is populated a little. Okay? Good.
And for average energy, you just use that n for the
N times h bar omega will be average energy. Well, n plus 1/2 times h bar omega. Yes. It would be also very interesting and useful just to inspect the value of n divided by n plus 1, but I will leave it for the class. There is a simple algebra, and by doing this fraction, you will get the Boltzmann. Which means that amount of energy going down is this times more probable than amount of energy goes up in our selected system. Enough. Let's look on the codes. So let's look on the code with name RDM underscore red subscript 1. And it doesn't show me right now. Let's focus it on you. Okay, So the code is originating from the same family of codes that we were discussing for several labs in a row. So it is propagation of density matrix element for two-level system. And originally we set up that occupation of ground state is 1, no off-diagonal elements, and occupation of excited state is 0. Then we do introduce the equation for number of quanta in the bath mode. So right now it is in the line 29. Then we do have well, let me suggest that instead of setting up different initial conditions for density matrix, we will always start with ground state, but then we will prepare realistic excited state by a pulse, so that we are more closer to reality. So another, in line 52, we set up relaxation parameter. Here it is just made up from the top of the head, but if you do it professionally, this is the major deal, just to find the rate of relaxation. And one typically does it either by ab initio or getting some serious arguments, like from heat capacity, distribute number of degrees of freedom. So there are some ways to estimate this relaxation parameter. Now, next, we do have our Liouville superoperator that we do not care much right now. It is more important if system is irradiated by light. But here we will need it just during the time of the pulse. And next, here is the most important thing. Here is the Redfield superoperator that is composed as matrix 4 by 4, and most important elements are in the upper and lower left and right corners. If you see, they are plus and minus relaxation parameters times number of quanta with number of quanta plus 1 if we are describing relaxation from excited to the ground. And it is proportional to just number of quanta if we look for thermal excitation. And then the line 66. Originally, it was formulated as infinitesimal propagation during time d tau of density matrix by applying this evolution operator, exponential to the power of Liouville operator times time. Now we add Liouville plus Redfield superoperator. That's it. Now let's run and see what happens. On your computers, probably it has been completed a long time ago. And when it goes for saving information and computing at the same time, it is heavy. Yes, yes. I probably can just focus on the image and pretend that it was computed. Hmm? So what I will ask you to do, first we will discuss it a little, and then you will try to change the values of temperature and relaxation parameter and see how it reflects in this dynamics. So what do we see? What do we see here? The pulse is set up at time 0. And the dynamic starts at time like minus a couple of thousand. Right now, nothing is changing to the system before the pulse, right? Is it the same in your when you run the code?
Mine decays a little bit.
Okay. If you do set temperature equals 0 or small fraction, you'll get the image as IC. You can do it quickly because okay. So if temperature is close to 0, then nothing happens to the density matrix until the pulse arrives. Then the pulse we set it up to be a pi pulse, so it performs inversion. It promotes all occupation from ground and to excited, and excited becomes 0 populated. So red is excited, blue is ground. And these dashed lines are off-diagonal elements, imaginary parts of diagonal elements. As time passes by, you see there is a relaxation that brings excited population back to 0 and ground population state back to 1, right? If we propagate it longer, we will see that as it will approach 0. So this is dynamics at 0 Kelvin temperature, but it is not the whole story. Often we need to take into account effects of temperature, of finite temperature. So let's go ahead and change temperature parameter, which is in line where? 28, thank you. Yes. If you set it up equals 1, then probably it is what was originally set up and what you have seen. Does it reminds what you see on your screens? Okay, so 0 and 100% occupation is not a thermal equilibrium state. So even if we do not have a pulse, we just do have influence of the heat bath of the thermal hot plate. It will thermalize and it will excite a little bit from ground to excited. So here it is about 20%. So the occupation of ground state raises by 20% and occupation of ground decreases by 20%. And then it reaches a thermal equilibrium. Then we apply pulse and it performs inversion in respect to thermal equilibrium. So it cannot excite away from the range that it is determined by thermal equilibrium. If it was like 20 and 80%, we cannot go back to 0 and 100 because the thermal bath prevents us from doing so. So we can only perform inversion compared to thermal equilibrium. And then it relaxes back, not to the ground and excited, but to the thermal equilibrium.
So if we did the pulse before it thermal equilibrium, we could get it back to the value of the opposite.
Yes, but then it would be very strange, exotic, and difficult experiment. It means that you prepare your system in absolute vacuum at 0 temperature, like in space or in supercooled liquid helium. Then you, in few femtoseconds, you bring it up to room temperature. In next few femtoseconds, you irradiate it with light, and then you look what happens. Typically, it is not the case. Typically, it stands in the thermal equilibrium for a long time, and it is prepared there. Make sense? So now please play a little with parameters. And I have a specific question that you may answer by numerical modeling. if system is in thermal equilibrium, in absolute, at infinite temperature. Here infinity can be equal 5. Is it possible to change anything in the system by an optical pulse? Can you please, your intuition and my intuition tells that no, but please try. And also, if you can, please make screenshots and plug them into PowerPoint. Pi? But if you discover that pulse of another area can violate thermal equilibrium, please report. It could be a good discovery. So please create a little PowerPoint with evidence of the hypothesis offered by Levi.
PowerPoint. I'm sorry for sound. The symbol.
I would do a question
Then it makes it look fun. No, you want to start at 0. We started at 0.
No, the code started at 1.
Yeah, but use this as 0. I'm doing I'm here. So it's 0, then 1, then 5, then 3. Almost. What?
just pulse. The variable pulse is set up for 6 at 0 for 1 pulse range, where the resulting pulse is centered. It's not amplitude, it is the position. Instant of positions are important. Instant of time.
Oh, I see. But I already asked that question. He said that's not realistic. And then it was still polarized. I guess I just.
100 is 10 is super high.
I'm going to do 0, 1, 5.
I think at 10 it changed.
And did you observe that at higher temperature, it's not just which is thermal equivalent, which is a quick. When I saw it for the first time, I was so surprised that strong powers that change everything. That's not. So if you are dumped to the center of the box here, there is no way to get out.
So you're telling me thermal equilibrium is a black hole?
Yes.
And lower it in so then you can get sufficient kinetic energy to get out of the black hole, like they did in what's that movie, Interstellar? I thought it was a great movie. Hey, it's not that bad. Dimitri, have you seen Interstellar?
No.
Oh,
You recommend?
I know it's very interesting. Oh my gosh, it's not that bad. What would be? When they were